All right, all, we are back again with week 3. We are moving into chapter 4, Newton's laws, exciting stuff. You will notice if you have looked at my solutions that I posted online that I apparently just decided for set 8, I didn't want to do half of them. I'm not sure how I skipped over them, but I did. So if you go back and look now, I have just kind of tacked them on the end. So if you've looked at them already and they weren't there, they're there now. Just kind of got to scroll down. But for this video, we're going to pretend like I just did them normally. We're just going to, as we solve the problems, we're just going to finish all of them. All right. So Newton's laws, chapter 4, number 3. A 6.0 kilogram object undergoes an acceleration of 2.0 meters per second squared. They're not even trying to come up with a story. It's just, here's the object and it's accelerating. So A is acting. What is the magnitude of force? So we're looking for F. And what do we know? M equals 6.0 kilograms. And A equals 2.0 meters per second squared. And we know Newton's second law, which is force equals mass times acceleration. We can plug in the values we're given. So 6.0 times 2.0. We get 12. We get 12, but we get 12 kilogram meters per second squared, which is just a Newton. So our answer is just 12 Newtons. Our force is 12 Newtons. Simple enough. All right, so moving on to B. B says if the same force is applied to a 4 kilogram object, what acceleration is produced? So we have Newton's second law. Well, no, we're going to start with what we know and what we need and what we're given. So we need acceleration. We are given force. We are given mass. Always start with what we know, what we don't know, what we need, potential equations we could use. So again, we've got Newton's second law. Know it, love it. Force equals mass times acceleration. This time we are solving for acceleration. So we want to rearrange this to solve for acceleration. And in order to do that, we're going to divide both sides by m. We're going to get A equals F over m. Plugging in the values that were given. So Newton again is kilogram meters per second squared. And mass is 4.0 kilograms. We're going to see that those cancel and we're going to get 3.0 meters per second squared, which is the unit that we're looking for. And that is our answer. Acceleration is 3.0 meters per second squared. All right, that one was pretty straightforward. Moving on to number 7. This one's fun. And another very straightforward. All right, so 7 says we have 4 forces acting on an object. So here's our object. Let's use different colors to look at our different forces because, you know, it's fun. So our first force, well, let's say first, let's define our directions because that can change depending on which way we're facing. Okay, so we've got a force is pointing east. So A is screen froze here. Here we go. Okay. So A is 40. B is 50 north. Ooh, let's do the fancy star one. C is west. And D is south. It's the biggest. All right. What is the magnitude of the net force on the object? So we're just going to add these forces together. So net force it's an A, right? Yeah. Net force is sigma F. I didn't actually look at the book at all or your lesson for this. I apologize. If you haven't seen sigma going forward, I will just leave that out. Confusing for anybody, but I will look at your textbook and how professor is teaching, and I'll see if he uses that. And if he does, I will bring that back. Basically, sigma just means add it together. So we're going to sum everything together. And that's FA, FD, FC, FA, and B. So let's come up with an X and Y component and then find the magnitude will just be will be the hypotenuse of the triangle that we've made. So let's start with adding A and C together. So C is 70 west. We'll say that A is in the positive and C is in the negative direction. A is 40. Net in the X direction is going to give us negative 30. So if we were to draw, this is going to be our addition of our forces. We're going to have negative 30. So 10, 20, 30. All right. Resultant force is going to look like that. All right. So now let's look at giving ourselves a Y component. We're going to add D, and D is 90. So we're going to say that B is in the positive Y direction and D is in the negative Y direction. So we're going to say negative 90. And B is positive 50. Going to give us a net of negative 40. So if I were to draw here, negative 40 right here. Our resultant, the magnitude of our net force is going to be this. It's going to be the hypotenuse of our triangle. And if you recall, A squared equals B squared plus C squared. So this is A and this is B and this is C. So we're going to say A squared equals B squared plus C squared, or A equals the square root of B squared plus C squared, which is the square root of 30 plus 40 squared. And you get 2,500. Square root of 2,500 is 50. So the magnitude of our force is 50.0 newtons. All right, B. He says what is the direction of our force? So if we are to draw our triangle over here. We are down and down. Sorry. This and this. Okay. So if we are to draw our triangle here, direction basically means we're looking for theta. So we could express that as north of west. We could say it's so many degrees below the negative x. We could say it's so many degrees from the negative y. We could say, we could just give a degree, and then we're assuming that we are, if this is our xy, we're assuming that we're starting here and going around. But really, we just need this angle is what our direction is going to give us. So we said that our resultant force, our magnitude is 50. So we know the hypotenuse of our triangle is going to be 50. And our x was negative 30. So this is 30. Now, to be exact, we would say this is negative 30 and this is negative 50, but we are just looking for that angle, so it doesn't matter as long as they match. All right, so we know that cosine of theta equals opposite over hypotenuse. Sorry, adjacent over hypotenuse. So we have 30 over 50. So we have all right, and if you do your math, you come up with 53.13 degrees. Now you could say 53 degrees south of west, or you could just say that your angle is 233. We would add the 53 onto the 180 it takes to get from here to here. So that is your answer. All right, so that's it for that problem. Number 11. Number 11 says a boat moves through the water, two forces acting on it. So we've got a little boat here. We have one force that is pushing it forward, which is our propeller force. The propeller force. And then we have one, which is a resistive force due to the water, which is really friction pushing us back. So we then have FR. All right. So our first question is, what is the acceleration? So in order to find the acceleration, we are going to have to find what the net force is. So we got one going this way and one going this way. We are assuming that if we have a propeller on our boat, that the propeller is strong enough to push our boat forward, and that the current of the water is not pulling us back. So we're going to say for sure we know that acceleration is moving forward. But let's add up our forces here. So if propeller's going forward, resistance is going back, we can say that our propeller force is in the positive direction. So we're going to say our net force equals FP plus FR. Which is 2.00 times 10 to the third newtons minus, if FP is going forward, FR is going back, 1.80 times 10 to the 3 newtons. All right, so A is asking us for acceleration. We now have force, the net force equals 0.2 times 10 to the third, which we would really say is 2.00 times 10 to the second. And the mass of the boat is given as 1.00 times 10 to the 3 kilograms. So we again know F equals ma, Newton's second law. We are solving for acceleration, so we're going to divide both sides by mass again, and we're going to get A equals F over m, which is going to be 2.00 times 10 to the second newtons divided by 1.00 times 10 to the third kilograms. Remember, Newton is kilograms times meters per second squared. You can see then that these cancel out, and we're left with an acceleration of 2.00 times 10 to the negative 1 meters per second squared. So a really simple way to do problems that have these exponents where, you know, it's 10 to the, so we get 10 to the negative 1 here. When you're doing really big problems that have a lot of constants, you end up with these huge equations that have 10 to the 8, 10 to the 32, 10 to the negative 11, 10. The easiest thing to do is to take out all the I can't think of it. Word, forgive me. All of the numbers, we'll just call them the numbers. So the 2.00, the 3, 1.0 here. So take those out and we get 2.00 divided by 1.00. Do the math there. So 2.1 equals 2, obviously. And then do the math of the tens. So if we do the math of the tens, we have 10 squared over 10 to the 3, but 10 to the 3 in the denominator is really just 10 to the negative 3 in the numerator. So this is really 10 times 10 to the negative 3. And we know that when we are multiplying exponents, we add them. So this is really just 10, 2 minus 3, and we get 10 to the negative 1. So you get this and you add this. So our acceleration is 2.00 times 10 to the negative 1 meters per second squared. All right, so that is our A. What is our B? If our boat starts from rest, how far will the boat move in 10 seconds? All right, so now we're using Newton's law, and then we're going back to our kinematic equations that we used last week, 2 weeks, I think 2 weeks ago. They were introduced, but we are going to use them in perpetuity now that we have the kinematic equations. All right, so B says, if the boat starts from rest, how far will it move? So we're looking for delta X. If the boat starts from rest, that means VI is 0. And they're giving us a time. All right, so this is what we have. We found our acceleration last in A. So now we're going to look at our kinematic equations, which I can pull up here quickly. All right, so here are kinematic equations. We don't have VF. So if we look at our not given, looks like this one here, looks like the one that we are going to want to use. And it says we're solving for, we need delta x. That's our man, as they say. All right, I don't know who they is. So the kinematic equation that we chose was this. Sorry. So our VI is given as 0. So this goes to 0 and it just goes away. And we get delta x equals 1/2 times a t squared. 1/2 is 2.00 times 10 to the negative 1 t squared. Oops, I put t equals seconds. That's not true. 10 seconds. 10 squared. And if we do our math here, we come out with 10.0 meters. All right. C says, what will its velocity be at the end of that time? So now we're looking for VF. So we go back to our kinematic equations. Now we kind of have almost everything that we need to solve anything in this equation. We have almost everything has been given. Now we need VF. We've been given delta x, we've been given VI, we've been given T, or we solved for A. So any of these are going to work for us. We're just going to choose whichever one seems easiest to us. This one seems pretty easy here. So let's use that one. And we're going to have delta x equals VI plus VF all over 2t. Basically, we're just finding VI divided by 2. We're finding what the average velocity is between the two beginning and end. We have constant acceleration though, so we know that the average is going to be what is going to be correct. Okay, so we're solving for VF. And we have 2 times 10.1 meters divided by 10, cancel, minus 0, and we end up with 2.00 meters per second. Right. Pretty straightforward. Moving on to 21. 21 says, car of mass 875 kilograms is traveling 30 meters per second when the driver applies the brakes, which lock the wheels. The car skids for 5.60 seconds in the X direction, coming to a rest. What is the car's acceleration? All right, so A tells us we're looking for A. What do we have? We have mass of the car. We have our VI. Car comes to a stop, so our VF is going to be 0, and our time is going to be 5.60 seconds. And we're looking for acceleration. All right, so we're going to look at our kinematic equations. We're going to figure out which is the easiest one to solve. This is going to be our easiest one to solve because VF is 0. Plug in a number, 0 minus 30 all over 5.60 seconds. Get 5.35, blah, 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 blah. Or A equals negative 5.36 meters per second squared. What is a negative acceleration? Negative acceleration means we're slowing down instead of speeding up. Here's our answer. Now that we've got acceleration, I bet we're going to use Newton's second law to solve for force. What is the magnitude of the force? Can I call it or can I call it? I did already do these problems, but I did them a while ago, so I really was just guessing just because. That's what we're doing here. We're doing Newton's laws, forces, forces, forces. All right, we're looking for force. And we are given mass 875 grams. And we were given acceleration. No, we found acceleration of 5.36 meters per second squared. Punch that into your calculator and you get negative 4,690 newtons. What does the negative force mean? A negative force means it's pointing this way instead of this way, if our direction is this way. But it asks for the magnitude, and magnitude means that it is an absolute value. So we're going to have this. All right, there we go. Number C, how far did the car travel? Delta X. All right, again, we're going to go and we're going to look at our kinematic equations. Which one is going to be the easiest? The easiest, I think, is this one, because VF is 0, and so then it goes away. T squared. We're going to punch everything in. Equals 0 minus 1/2. Acceleration we found 5.36. Time was given as, I forget, 5.6. All right, and you punch that into your calculator, and your answer is 84 point blah, 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 84.0 meters. That's fun. That one used our kinematics equations and Newton's second law. Like it. All right, so here come the questions that I apparently just decided I didn't want to do, skip right over, but I did them today, earlier this morning. All right, so the first one is 85. Let's take a look at 85. We gotta skip through the book quite a bit. Ooh, an Atwood machine, those are fun problems. It's not this problem, there's scrolling through. All right, so 2 boxes of fruit on a frictionless horizontal surface are connected by a light string, as in the figure, where M1 is this, M2 is this, force is this. All right. A, determine the acceleration of each box and the tension in the cord. So let's draw a little picture here. We've got one box. This is M1. We've got box 2. This is M2. They're attached by a cord. Someone's dragging it. And we're looking for acceleration and tension. So the tension is the force in that string. The force is moving this way. Tension then is going to be moving this way because it's pulling that forward. All right. What are we given? We're given mass 1 equals 10 kilograms. Mass 2 equals 20 kilograms. And the force, or the person pulling it, is 50.0 newtons. So let's start with A. A is super simple. We've got F equals ma, as we've already shown. F over m is how we solve for acceleration. So of course we've got 50, but our mass here is actually not given because our mass is going to be m1 plus m2. In the problem, they say a light string, and what they mean by a light string is that there's no mass to the string. It's not adding any mass to the system. So our m is actually going to be m1 plus m2, which is going to give us 30 kilograms. So we've got 50 newtons over 30 kilograms. And again, kilogram meters per second squared. These are going to cancel, and we're going to get 5 over 3 meters per second squared. That is an answer, or you can write it in terms of a decimal, and that's going to give us 167 meters per second. All right, now the tension in the string. So how are we going to solve for the tension in the string? So if we look at just this system has tension, so a force, and the mass of that box. Neglecting what's happening afterwards, just looking at that, we're going to have force equals mass times acceleration, where the force is just this t. So tension equals mass times acceleration. Acceleration we solved for last problem. And mass is 10 kilograms. So we end up with 16.7 newtons, and that's the tension. Right. So the problem says only solve for A. I think the next ones, they add friction, which we're not going to talk about until set 9 or 10, I think. All right. So 85A, got it. Moving on. Now we're going to look at 24A. So now I got to go way back. All right. 24 says a block of mass M, 5.8 kilograms, is pulled at an angle of 25 degrees at an incline with a force of magnitude F equals 32 newtons. A says, find our acceleration if the block is frictionless. Okay. So these problems can get pretty ugly with the force diagram and lots of arrows and whatnot. So let's try to make this colorful. Okay, so here's our box. This is our mass. We only have one. So let's make a force diagram of this box and all of the forces that are acting on it as it's being pulled up this incline. So the first one we're given, and that is just the force that's given. That is someone's pulling this up or pushing it up, force going in the up direction. So we've got F. So we are relatively close to the center of the earth. So of course we have gravity pulling her down. Gravity, we can just say is mg. Gravity is always going to be mass times the acceleration due to gravity, which is g. Anytime you have a mass that is sitting on something and not seeping into it, we have what is called the normal force. And really what the normal force is the electrons that are in the table or floor or incline here. It is the force of the electrons' negative electromechanical force pushing up, and the electromagnetic force in the block, so the electrons in the block are also negative, so they're going to repel each other. So really the normal force is just the electrons going, ugh, you're not coming in here. So normal force is always going to be in the opposite direction of what you're sitting on, because electrons are just pushing you out. So normal force, let's do normal force red. Normal force goes straight up from the surface. What else do we have? So that's pretty much it. These forces are pointing in all different directions. This really doesn't help us find acceleration is the first thing we want to find. It doesn't really help us find acceleration. So what we have to do is we've got to piece this apart to make triangles to find the forces that we want to look at, the X and Y components, so that we can solve for F here. So there are a number of ways to do this problem as far as figuring out what you want your origin to be. So anytime you have a problem, unless the problem specifically says start, here's your origin, you can choose your origin. You can choose where you want how you want to lay your coordinate system. And of course, we always want to pick the easiest. So if I were to make a coordinate system that looks like this, and here's my origin, that's really stupid. That's not going to help us at all solve for this. So we could just do like, this kind of seems like, oh, that looks like what we should do. That's where the incline starts. But then we have to break everything into its X and Y components, and we can do it that way. We can do it any coordinate system that we want, but that gets kind of messy. We are trying to solve for acceleration up the block. So what if we were to make this our origin? So if we were to draw like this, now our force is pointing in the positive F direction. We need to find this, the magnitude of gravity that is pulling us down in that direction. And that is basically what we need to solve for then. If we were to choose our coordinate system as I first drew it, we would have to find coordinates in the normal force. We would have to find both coordinates of this. mg is only in the y direction, but that would very much complicate our problem. Here, we're just solving for the x because basically that's what we're looking at. That's our x. Okay, so we know, of course, F equals ma. The force we're given in the positive x direction as 32. We're given theta is 25, and we're given our mass as 5.8 kilograms. All right, so force equals mass times acceleration. Mass, we just have the mass of the block. Acceleration, we just have the acceleration of the block. Forces, we have a couple forces at play. Normal force, we don't even have to look at. We would if we were taking friction into account, but we're not. And so really what we need to look at is this component of gravity and this. So we've got, let's say FG plus the F applied equals mass times acceleration. Okay, so how do we find the component of gravity that we need? So the triangle is a little bit ugly here. Let's see if we can draw it a little bit better. So, all right, so here's our triangle. So this is going to be mg. Now, what is our angle going to be? This gets a little bit complicated, but we got to think about it a little bit. So we could take this as our theta, but we don't know what we would have to solve for it. If you look at our little diagram here, this angle is going to be, so let's call this alpha. So theta plus alpha is going to be 90, because this is a 90-degree triangle and triangles have 180. 90 is 90 degree of one. So these two are going to be 90. So this right here, we could solve for with the theta that we were given, but in the triangle that we've drawn over here, this is going to be alpha. But if this is alpha, then this must be theta. And if you've ever taken a geometry class, I remember from high school, we did all of these proofs where if this line crosses through and yada, yada, yada. There are lots of geometrical proofs. This one, I remember this one specifically, but here's why. If you look at it, here's why this angle, the angle that would be here, is going to equal that. All right, so anyway, we want this. We want right here, this, which is going to be this. And we know that sine theta equals opposite over hypotenuse. Hypotenuse is going to be mg. So we've got mg sine theta equals x. So, and our x is the FG component that we want. So FG is mg sine theta plus the applied force that we're given equals ma. All right, so we're solving for acceleration, right? Solving for acceleration. Mg sine theta plus the applied force divided, holy cow, divided by m. Plug in what we've got, 5.8 kilograms, and you actually don't have to do this. You can cancel those two out and redraw it a little bit, but this I'm just gonna write it out because this is how I've drawn it. All right, so if you plug in numbers here, you end up with, there, you end up with 1.37, and we need 2. So 1.4 meters per second squared. All right, so there's our answer. All right, so B, oh, this is friction again, right? Oh yeah, we're just solving for it. Okay, 25. Moving right along. 25 says, a rocket takes off from Earth's surface, accelerating straight up at 72. So A equals 72.0 meters per second squared. We get a little rocket. Calculate the normal force acting on an astronaut of mass 85. All right, so we've got force going up with acceleration. We've got mg going this direction. So our normal force not only has to hold us up from gravity, now we've got a super fast acceleration compared to gravity. And the normal force has to overcome that too. So the normal force is going to be relatively high for what we would see standing on the ground or putting our hand on a table. So our normal force is going to be both of those forces. It's going to be mass times acceleration plus mass times acceleration or gravity. So we've got mg plus ma, which is 85.0 kilograms times 9.80 meters per second squared plus 72 meters per second squared. And if you plug that into your calculator, we get the normal force E is 6950. Now, just to quickly look at what that means, the normal force of like the ground pushing up on my feet if I weighed 85 kilograms. If I'm not accelerating, it's going to be 85 times 833. So 833 newtons is the force of the electrons pushing you up relatively close to the center of the earth, just standing around. 6950 is what it is for this rocket. And so if you are in a vehicle that's accelerating, you notice that you kind of fall into the seats because it's not a super rigid material. The electrons aren't super pushing you back. So there's a little bit of give before the electrons go, get out of here. All right, so there's our answer. That is our last problem. I will see you again for set number 9, which is where I believe we start looking at friction.